Welcome to the MOOC course on smart materials and intelligent system design. In the last few lectures, I have talked about piezoelectric materials and magnetostrictive materials. Now, today we will be taking up a new material. So, just in the last lecture, if you remember, we have talked about what is magnetostriction, we have told you about a brief history of magnetostrictive material, so that you know how such materials have evolved, and we have discussed about different effects of magnetostrictive material. So, in this lecture we will take up a new material now, which is active smart polymers. Okay. So, we will talk about that what are these group of active smart polymers and what are the different classifications of these electroactive polymers, a particular group of it, and what are the applications of it. Now, what is the reason for us to go for these active polymers? One of the important inspiration came actually while we tried to simulate the or emulate, so to say, the animal locomotion systems. Okay. So, the first series of rigid robots, if you look at it, that there were these robots of like quadruped stair climbers. Okay. They are quadruped, but they are not good like the animal to mimic the animal behavior, because they were not like the real legs. People get somewhat more towards the real system when they could develop something like a snake like motion in ACM R5, one of the examples, and even more sophisticated when they could develop actually a bipedal walking robot, M2 or other robots are such examples. But one of the thing is that in all these robots, the locomotion was achieved from actually motor based rigid robots. They were not muscle based. On the other hand, animal based systems are muscle based. So, the point is that can we develop a muscle based locomotion system? Now, active smart polymer can actually do that. This type of polymers can respond to external stimuli by changing shape or size, and that change of shape is really very high. I will show you later on, and these are known as active smart polymer. Now, this type of polymers are generally we divide them into two categories. One is simply active polymer, in which these these input stimuli that we apply can need not be just an electric field, it can be pH, it can be magnetic field, or it can be light. Okay. For example, anionic cellulose PACs, okay, they are one of the groups. I will show you some of the groups which can be actuated by using light photostrictions. So, active polymers can take basically any inputs, and it is not a electrical input, non-electrical inputs like chemical inputs, magnetic inputs, or light as an input. Electroactive polymers, on the other hand, respond to the change of electrical input, and that is why they are known as EAP. So, we have active polymer AP, and we have a special group which is EAP, which actually gets actuated with the help of electric field input. Now, one example of active polymer, if you look at this, that in this particular system you actually have, this is based on azobenzenes, okay, azobenzene group, which contains these double bonds of nitrogen, okay, and the moment you apply a visible light, say for example, then this double bond reacts in a manner that it actually bends. So, there is a seize conformation in it, and when you apply the UV light source, not the visible light, then it goes to the trans mode. So, by varying the UV and the light source, so for example, in plain light you can see that there is this bend there, okay, and you apply UV, you see that the bends are opening up, it is getting flattened. Again you apply light, again it is bending actually. So, bend flat sequence can actually generate some kind of a inchworm motion. So, this is a light actuated motion that you can generate in such a system. Now, if you compare between the electroactive polymer, not the other activation, but electric energy as an input. So, if you compare the performance of that versus other piezoelectric materials that are generally used, like say shape memory alloys or like say electroactive ceramics, you would see that the actuation strain in electroactive polymers is about 10%, which is much higher than the shape memory alloys 8% and much higher than any of the electroactive ceramics, which is only 0.1 to 0.3%. 10% remember is some kind of a change you will be able to see even simply with your eyes itself. So, it will be very much visible. I will show you examples when you will see, you will be able to see that. But what is the flip side of it? Deformation is very large, but the force is actually quite less. It is about 0.1 to 0.3 megapascal, whereas SMA you get a much higher force and considerably high force in electroactive ceramics. The reaction speed is also moderate or at least comparable to the electroactive ceramics. Density wise they are very light. Driving voltage wise it is low driving voltage, which is good because electroactive ceramics need much higher voltage. Shape memory alloy wares need some kind of voltage of the range of 10 volts or so. It is actually a current driven process, and the power it consumes is about milliwatt range, and it has a good fracture toughness, resilience, etc. So, only the negative side is the force development, that is the minus side of it, and to some extent the reaction speed. Otherwise, this is full of positive things which are worth of actually venturing. That is what is our motivation to study the electroactive polymers. Now, among the electroactive polymers or EAPs, we have two groups. One is called EEAP, that is electronic electroactive polymer, and another is called IEAP, that is ionic electroactive polymer. If you look at EEAP, there are typical examples are like dielectrics or electrostick papers, ferroelectric polymers like PVDF, for example, I have shown you in one of the earlier classes, liquid crystal elastomers, these are all EAPs. If you look at IEAPs, ionic polymeric gels, IPMC, ionic polymer metal composite, also known as IPMC, this is what is very popular. I will mostly focus on this today, conducting polymers and even carbon nanotubes. So, these are the group of ionic electroactive polymer. Now, naturally one of the important aspect is that here the phenomena is at the electron level. So, it is a electronic movement or changes, so to say, which generates this effect. On the other hand, here it is at the ionic level. So, the speed is little slower in comparison to the electroactive polymer. So, if we look at the comparison between the two, electronic activation of course needs a higher actuation voltage, but here you need a low driving voltage, but here the energy density is high and rapid response time, whereas ionic electroactive polymer it will have a little less slower response time. But of course, the amount of deformation will be much more, because particularly under wet condition, because the large scale ionic movement in the form of in fact movement of water jetting out will create a huge change in the shape of the system. So, here is one of the very popular application, that is particularly for space applications, that you can use these things for creating dust wipers, because you know that many of the rigid body wipers they always have some of the blind spots which they cannot clean. That is because the links are of fixed geometry, they cannot change. On the other hand, for electroactive polymers you can change the length of the wiper. So, that means if you take a rectangular spot, a rectangular block, you can clean the entire rectangular block, whereas with your so called, if you look at the car wipers with this type of a system, there will be always some corners. So, for example, this type of corners which you will never be able to clean properly, or these corners. So, that is why as a dust wiper, particularly for space shuttles, this is of very good use. The other use is in terms of sample handling. You can use these things to actually use like fingers, like artificial fingers. There are plenty of applications of such a system in mechanisms, in lenses, mechanical clock or noise reductions, etc. Just to mention a few, the list is in front of you. Robotics in terms of toys, animations, there is something called biologically inspired animations, okay, mechanical animations or mechanimas. So, where you can animate the object in a way which is almost like a real world situation, and that you can do with the help of electroactive polymers, because you can achieve large deflection in a compliant surface. So, that is why it is used at a very high rate in animations. It is also used in various human machine interfaces, like for touching, tactile interface, or for orientation, or for diving suits, etc. Planetary applications I already talked about. Medical applications, particularly one application is becoming very active in the research front, that is in terms of developing drug actually injections. So, a controlled drug release in a system can be done with the help of electroactive polymers. Also, it is used in liquid and gas flow control, controlled weaving, MEMS based systems, and various other sensors and transducers. Now, if you look at one of the most popular electroactive polymers, which is I told you the IPMCs, then it works like ion exchange polymer, and if you have deposition of particles here, okay, you can actually make a metallization of them. So, you can make a polymer in such a manner that it is partially metallized. Okay. So, this kind of a thing will actually help to develop cathode or anodic terminals in a polymer. As I told you that we have to at the end look for a high movement of water, okay, inside the system, going in or going out. So, towards that direction, to control that high cationic movement, metallization is very much necessary to see the electroactive effect. Now, if I focus on one of the most important ionic polymer, which is known as Nafion, then you would see that it is having actually a polymer matrix which is sandwiched between two metallic layers, okay, like these two electrodes formations that I have shown you. And Nafion itself is having actually a PTFE structure, which is also known as perfluorinated copolymer of PTFE. So, you can see the presence of fluorines and the carbon main chain, which actually gives the source of strength to the system. In addition to, you have a perfluorinated vinyl ether sulfonate, which is this part. You can see that this vinyl ether sulfonate part, which is the source of polarity in the system, the sulfonate group. So, in a sense, you have a polymer which gives you a high strength due to the presence of this perfluorinated system. Perfluorination is a process where all the hydrogens that is there, say for example, you think of ethane, methanes, etc. So, all the hydrogens from these areas are actually completely replaced by fluorine. Okay. That is what is perfluorination of the system. So, perfluorination gives us a better strength, and in addition it gives us a polarity, and it can hold actually the sulfonate groups, and that is used in terms of picking up these ions that we are talking about. So, how does an IPMC work? Well, first of all, it consists of a fixed network with negative charges, okay, and that is coming because of the presence of the sulfonate groups that we are showing here, and it is balanced by mobile positive ions. So, whenever I am subjecting this system to DC voltage, okay, I am generating a voltage, what will happen is that there will be these cations, okay. These are the mobile positive ions which will go towards the cathode, and water molecules which are mostly in H plus and OH minus. So, water molecules will move then towards this side, causing a hydrophilic expansion of one of the sides. So, as you can see here that as we have applied the voltage here, and you can see that there is a fixed network, and you can see the movement of all these water molecules, okay, and causing a hydrophilic expansion. So, this is a fixed anion, the blue ones are all fixed anions, and these are the mobile cations as you can see, okay, and you also have waters here, okay, attached along with the mobile cations, and you have these as the hydrated cations. So, as along with these mobile cations, the water molecules are also moving towards this direction to the negative side, you are getting an expansion in this direction. So, this is something which creates a large change of shape in the system. Now, what will happen if all negative charges go towards one direction? They will gradually start to repel. So, there will be a back diffusion that will happen in the water molecules. So, which will cause a slow relaxation towards the cathode. So, extent of accumulation of these will depend on what is the type of polymer we are using, what is the type of ions, presence of moisture, and the quality of my metallization, how good is my cathode and anode terminals. So, this is how then IPMC system works. And if you look at a IPMC composite, then you can see that in this particular IPMC system, for example, that as I am applying the voltage in the system, okay, how this bending is taking place in the system, and this is in reality how you will be getting it in say Nafion or this type of similar IPMC systems. We can actually, by selectively choosing these electrodes, we can actually make a double bending system also. That means, two different types of electrodes, so that the cations change the polarities, then you can actually get deflections in two different sides. So, you can generate actually both directional bidirectional bending in the system by choosing electrodes suitably. So, that is a strategy that many times is used. So, that is one of the strategy of developing the double curvature using IPMCs. Now, the way it is done is that suppose you put AU coated part in one of the electrodes and the other part is dodite coated. Okay. So, this is the material here inside is Selemion instead of Nafion, it is Selemion, which is an ion exchange membrane and it is manufactured by Asahi Glass. It is very popular. So, you apply gold in electrode in one side and dodite in the other side, and what you are going to get is actually a bidirectional bending, exactly what I have shown you in this case. So, with a material Selemion you can achieve this. Okay. This is one of the strategy of double bending in Selemion. Now, IPMC based actuators specifically, they are used for various purposes like single link manipulation, like multiple link grippers, vibration generation and control, and for 4-bar manipulations. So, if you look at one of the applications like single electrode flexible manipulator. So, in this case what you have is that you have a cantilever beam and you apply the voltage, accordingly you will see the tip point getting displaced. Okay. So, depending on the direction of the voltage, in this case you will see the reversible changes, and as a result you will see, if you start to plot, you will see that the distance from the fixed end you will see will be actually increasing, and the deflection along the y axis, that if you start to measure, you will get a kind of a workspace, so to say, or the end point movement. So, that gives us what is the range in which you can actually manipulate such a system. So, this is and you would see that the endpoints can be moved in a curve by controlling the voltage in the system. Now, I can show you how you can use it in the form of a gripper by controlling this. So, if you look at this, this is used for planetary missions by NASA. So, you can see controlling the voltage from this ends, you are controlling this bending and how you are actually using that in terms of gripping a particular system. So, like that if you have to pick up a different geometry, you can actually change the voltage, and it is pretty much reverse and robust and programmable. So, that is one of the examples in which you can use such a system. Now, we would like to talk about some of the other actuations, like what if I use 2 or more patches. Well, 2 patches I had already shown you that you can develop a bidirectional deflection in a 2 patch system, and this can be then used for a planar work volume generation. So, that is something in which you can use the strategy of that Selemion with gold androdite. Another interesting thing that can be done is if you develop a 4 bar system in which one of the link is actually flexible. So, then what you can do is that you can use it as a manipulator. So, this is the crank side, this is a coupler, and this part if you can change the length of it, you can actually use it in terms of developing various different work surfaces. I can show you one examples where these kind of systems can be used for actually developing artificial muscles. This is a polypyrrole which has gold based system of electroding. So, if you look at it, that how much you are able to change the shape of the system. So, you imagine I was telling you about drag release, that if you can generate this much of deflections at the end point, you can actually release the drags from a system by using this particular type of a actuation strategy. So, thus IPMCs can be used in various cases where you can actually generate large deflections, and as a result of that you can manipulate an object, you can do a pick and place of an object at a location, or you can use it for flow controls and purposes like that. So, this is what I would like to give as an overview for IPMCs. In the next lecture, we will talk about shape memory alloys, we will give an introduction to shape memory alloys, and we will also talk about relevant things like 1 and 2 way effects of shape memory alloy and applications of such shape memory alloy. Thank you.